All right, here we are again. Another lab. This time it's buffers, which come from acids and bases. It's a combination of the two. And again, like last lab, I'm going to do a little bit more in depth than you need to be able to do this lab, but I think it's important that you understand sort of the principles behind this. The labs are pretty simplistic for these acids and bases that we're going to be doing, but there's a lot more to them. I want to make sure you have a little bit of an understanding of that. So if you remember last time, we have our simple acid equation. That's HA plus H2O, and that goes in equilibrium to give us the hydronium ion, H3O plus A minus, the conjugate base. Conjugate base of a weak acid is a weak base. And we use Lavoisier's conservation of matter to say that the analytical concentration, that is how many moles of the acid goes in, how many moles of HA went in per liter, is going to be equal to the species concentration of HA, how much of it stays in the protonated form, plus the concentration then in the deprotonated form. In other words, put in 100 moles of this, 95 might be this, 5 might be this, but the sum of these two have to equal that. And then I can change that to say then that HA is equal to my CHA minus A minus. And the reason that that helps is if we look at our Ka is equal to the hydronium ion concentration times the A minus over top of HA, products over reactants. Remember, capital K, products over reactants, raised to the power of their coefficients from the balanced chemical equation. So this would be the equation that we're using there. So we have three unknowns. This is known. We're given Ka, and we know the analytical concentration, but we don't know these three. With this substitution, I can put this in for HA. I can change this to say that Ka is equal to H3O plus times A minus all over top of CHA minus A minus, right? Because I know that concentration. Then, as we talked about last time, we can make an assumption, and that is this is a weak acid, but the hydroniums that we're getting all come from that weak acid. The amount that comes from the self-ionization of water is pretty small, very, very, very small, so it's insignificant. With that assumption, we can say that the hydronium ion concentration is equal to the A minus concentration. Therefore, I can change this with that substitution and say that Ka is equal to hydronium ion concentration squared all over top of CHA minus hydronium ion concentration. And that's a quadratic. That becomes a quadratic in that hydronium ion concentration squared plus Ka times hydronium ion concentration minus Ka times CHA equals 0. That's our A, B, and C terms for our quadratic equation. We can solve for that, get the hydronium ion concentration, determine the pH, which is usually what we're looking for. Okay, so that's great. With a buffer situation, imagine that I had this weak acid and I have this established equilibrium that's going on. And now I add in a strong base, sodium hydroxide, let's say. Sodium hydroxide is a classic strong base. I add in a strong base. Well, sodium hydroxide obviously goes to give me sodium plus hydroxides. Well, these hydroxides react with hydroniums to produce water, right? That's the actual Kw. There's actually a Kw for that, and that is Kw is the 1.00 times 10 to the minus 14, and that's equal to hydroxides times hydroniums. So this is going, that comes from water. Two waters go to do that. So what that does is, you look at Lavoisier's principles. As I'm reducing the number of hydroniums, the reaction is going to shift to offset it, create more A minus, and reduce the amount of HA. So my HA goes down, my A minus goes up. And in fact, every mole of hydroxide added removes a mole of hydroniums, and the reaction shifts to offset that and replace the hydroniums. So for every mole of hydroxides added, I create a mole of A minus. And since I also have sodiums, that's exactly the same situation as if I had a solution that was made up of NaA and my HA, right? Because NaA is going to go to give me Na plus A minus. Okay, well, that's exactly the same situation I had up there. So my A minus then plus H2O would go to give me OH minus plus HA. Now that's the base reaction. We're not looking really at the base reaction. We're looking at the forward and reverse reaction possibilities. That is, let's go back to our balanced chemical equation for the acid. That is HA plus H2O goes to give me H3O plus A minus. Now I'm adding in a lot of A minus, okay? So I've got a lot of A minus. In the normal acid thing, I only had a tiny bit of A minus. Remember, we said that for every hydronium there was an A minus, but it only dissociates to a small amount. Here, we've got a significant amount of A minus and a significant amount of HA. Well, if I made up a solution of the conjugate base of a weak acid and the weak acid, I've got both of these in significant amounts. When I've got both of those in significant amounts, I can no longer say that the hydroniums created are equal to the A minus, right? Because it's not true. That's only true when the HA dissociates to produce my hydroniums. But now I've got to and make an A minus. Now I've got A minus in excess of that. So I can no longer make that assumption. Therefore, no longer any of that is true. What do I have to do? I have to go back and use my Ka is equal to H3O plus times A minus all over top of HA. And I say, well, okay, how can I use that? What can I do with that? Well, what I can do is I can rearrange this and solve for hydroniums. And I say my hydroniums now are equal to Ka times HA over top of A minus. If I know the concentration of HA, the acid, and I know the concentration of A minus, the conjugate base, I can solve this to get the hydronium ion concentration. Well, some smart fellows came along and they said, well, okay, but if we do that, why don't we just make it equal to pH, right? So why don't we just take the negative log of both sides, and we can say that pH is equal to pKa, because remember, P just means negative log of, so this is the negative log of the Ka. And if you know your rules for logs, if we take the log of two things that are multiplied together, it's the addition of the log. But this is the negative log, but we like to have addition, so I'm going to take the negative log of this, but also knowing your rule of logs, if I switch the A and the HA up and down, that changes it from a negative log to a positive log. So that's plus the log of A minus conjugate base over HA. And that's known as the Henderson-Hasselbalch equation. But really, it's just Ka. So you don't have to memorize the Henderson-Hasselbalch so much. If you just know Ka, and you know Ka because it's products over reactants raised to the coefficients from the balanced chemical equation, that's pretty easy. And then you just take the negative log of both sides and do a little bit of simple math, and you get the Henderson-Hasselbalch equation. Anytime you have a significant amount of weak acid and its conjugate base, not the tiny bit that comes from the ionization of the acid. That only gives you, like I said, 1 or 2%, maybe 3% of the acid goes that way. But anytime you have a significant amount of A minus and HA in excess of the natural dissociation from the acid, that's a buffer. When it's a buffer, boom, you say Henderson-Hasselbalch. Anytime it's a buffer, boom, Henderson-Hasselbalch. If you've got the weak acid and its conjugate base and they tell you the concentrations, boom, Henderson-Hasselbalch. This is what you're using. Every time, I don't think there's any exceptions to general chemistry too that would come up with. If you've got the conjugate base and the weak acid concentrations, boom, you're going to do Henderson-Hasselbalch, and that means you're going to use the pKa inside there. So let's go through and look at a couple of things about these, because one of the things that's really nice to do is to be able to have sort of, I don't know if you call them tricks or something, but things that we can use to check to make sure that we're doing things sort of correctly. So let's look at the handout. Let's see, we got some calculations of pHs for a mixed weak acid and its conjugate base. So we want to calculate the pH of a dilute solution that contains a molar ratio of potassium acetate. Usually when it ends with a tate, like that is the conjugate base of a weak acid. Acetate is the conjugate base of acetic acid. So you take the acetic and add the 8 onto the end, and that makes it the conjugate base of it. So potassium replaces the hydrogen on the acid, and it's potassium acetate and acetic acid. That has a pKa. They've already given it to us, but we'll make sure we know how to do that, of 4.76. Okay, so we want to calculate the pH of a solution that's made of 2-to-1 ratio of potassium acetate to acetic acid. Well, we're going to use Henderson-Hasselbalch. pH equals pKa plus the log of conjugate base over top of acid. So for number 1, we've got a ratio of 2-to-1. So we have pH is equal to 4.76 plus the log of, well, it's the ratio of the base to the acid, so that's 2/1. That's the log of 2. And if you plug that into your calculator and do the work, you should end up with 5.06. Now, one of the things we want to look at, is there was more base than there was acid here, right? It's 2-to-1, twice as much base as there was acid. Is our pH greater than or less than our pKa? It's greater than. If there's more base than acid, your pH needs to be greater than your pKa. If there's more acid than base, your pH needs to be less than your pKa. So that's kind of a way to check it. You look at it and you say, okay, it was more base than acid, and my pH is greater than my pKa. Okay, then there's a good chance I did the math correctly. How about this one? We want to do a ratio of 1-to-3. So that's going to be pH equals 4.76 plus the log, and this is base to acid, so 1/3. Now in this case, the acid is much, much greater than the base. Therefore, we would expect the pH to be greater than or less than our pKa. Less than. And in fact, it is. It should be 4.28 is what you should get. For number 3, and you can always pause the video and calculate these out before I do it to make sure you get the right answer. That's going to be 5-to-1. Again, in this case, and I won't go through the calculation again. In this case, will we expect the pH to be greater than or less than? Well, it's a lot more base than acid, so we expect the pH to be greater than, and in fact it is. It's 5.46. I guess I should do them as A, B, C, D, since that's the way I did them in the handout. For D, we have 1-to-1. Now, 1-to-1 is a very special case. Now, don't get confused. When it's 1-to-1, that means 50%, there's the same concentration of conjugate base as there is weak acid. You don't get a 1-to-1 ratio at the equivalence point. You get a 1-to-1 ratio halfway to the equivalence point. Imagine I put in 100 moles of HA. Well, halfway to the equivalence point, I then have changed 50% of this into A-, and so these concentrations are the same. If I go all the way to the equivalence point, I've added an equivalent number of moles. I've changed everything into A-, so that's not there. But you knew that the log of, this is going to be log of 1/1, and the log of 1/1 is what? 0. Therefore, pH equals pKa when it's 1-to-1, and that means it's going to be equal to 4.76. That's pretty easy. So anytime it's a 1-to-1, you know what the pH is going to be without even doing a calculator. How about 1-to-10? In this case, a lot more. An order of magnitude more acid than base. But remember, pH is a log scale. So if there's an order of magnitude more acid than base, what would we expect our pH to be? It's going to be 1 unit less, and our pH should be 3.76. And you can calculate it out using Henderson-Hasselbalch, and that's what you'll end up with. Okay? So that makes sense. So that figures all that. So let's do a couple of examples that are a little bit more involved. And like I said, what you're going to do for the lab is going to be very easy. You're going to be given you press a button that is going to select the pH point. And then you're going to move selectors up to give you a ratio of acid and conjugate base that gives you that pH. And you're going to write down that ratio, and then you're just going to calculate out using Henderson-Hasselbalch to verify that that is correct. So it's pretty easy. It's not as, we're going to be doing more difficult things here. So first question is, what is the pH of a 0.120 molar solution of NH4Cl. Now, you notice that has Cl, that's a negative ion. That's just the counter ion for the NH4. That's our acid. NH4 is our acid because it's the protonated form of ammonia. Ammonia is a base. Protonated form of it, that's going to be the acid. Remember the Bronsted-Lowry definition of acids and bases. And it's also 0.0300 molar in NaOH. Okay, we're not going to be doing any problems in this lab where you're adding NaOH to create the conjugate base. You'll be given the conjugate base. When you move the sliders, it'll give you the conjugate base form of it. But I want you to do at least an example of this to show you how to do this. So remember, for every mole of NaOH added, we create a mole of A minus. So in this case, we've got a Ka equal to 5.6 times 10 to the minus 10. All right. So first thing we need to do is we've got an acid. We're going to create a conjugate base because we're adding a strong base to it. So the first thing we need to do is figure out what the pKa is. How do we get the pKa? Well, the pKa is just the negative log. So the negative log base 10 of 5.6 times 10 to the negative 10 is equal to 9.25. Okay. So now we know we're going to use pH equals 9.25 plus log base 10 of A minus over top of HA. Okay, so I just got to figure out these two values. If I figure out these two values, I've got it. Well, I know 0.03 moles of NaOH. For every mole of NaOH added, I form a mole of A minus. So it must be pH equals 9.25 plus log base 10 of 0.0300 divided by HA. Well, I had 0.120 molar for HA right here, right? But for every mole of this added, one mole of this got turned into the conjugate base. So what goes down here is not the 0.120, it's the 0.120 minus 0.0300, because I have to subtract that got turned into A minus. Okay, again, we're not going to be doing this for the lab, but I'm sure you're doing this in class, and I want you to understand how to do that. Therefore, this becomes 0.0900. So that's what goes down, is 0.0900. Well, that's basically just 1 to 3. Didn't we do a 1 to 3? Well, we did, but this has got a different pKa. So when you calculate it out, pH equals, well, is there more acid or more base? There is more acid, isn't there? So we'd expect this pH to be lower than the pKa, and in fact it is. It's 8.77. Okay? All right. Do we need to do something with a... okay, I guess we can go through that really fast. I don't think you're going to do anything on that lab that has to do with multiple different things. But let's say we want to make a buffer, phosphate buffer. Well, phosphoric acid, is a polyprotic acid. It has three hydroniums on it. And therefore, it's got 3 pKa's. It's got pKa 1, which is 2.14. It's got pKa 2, which is 7.198. And it's got pKa 3, which is 12.4. So we want to make a buffer that has a pH equal to 7.02. Well, when you're making a buffer, usually the way you prepare a buffer is you find a weak acid that has a pKa very close to the buffer you want to make. And then you either add a little bit of acid to it or usually you add a little bit of base. You want something where it has a pKa that is either below or almost exactly what you want as far as a buffer. Well, somewhere close to where you want it. It doesn't have to be below necessarily. You want it usually within 1 pH unit of the pKa. And then you add base to it to create that buffer to give you the right ratio. So in this case, we have to say, well, which one of these 3 do we want? Well, this one has the pKa that's closest to it. So to be able to use Henderson-Hasselbalch equation, we need to know what is the values that are going to be in there. Well, that means we need to look at them. For Ka1, what is it going to be? It's going to be H3O, not H3O. It's going to be HPO4 plus H2O, the acid, plus gives me H3O plus H2PO4 just minus. I know I get ahead of myself on here. Okay, the first Ka is always for the first proton loss. The acid is H3PO4. The first proton loss gives us that. Ka2 is going to be for H2PO4 minus plus H2O, which is going to give me H3O plus HPO4 2 minus. Ka3 then is going to be for HPO4 2 minus plus H2O is going to give me H3O plus PO4 3 minus. These are the conjugate bases, which then become the acids for the next step. Except for the first one, that's the acid, that's the complete base. All right, so we're going to be using Ka2 because that's the one that's closest to it. That means we're going to be using this ratio of values. So we want to figure out what we need to be able to get that. So how would we set that up? Again, this is going to be much more complex than anything you're going to do in the lab, but it might be something similar that you're doing in class, so it's worth going through. So I have pH equals pKa plus log of, in this case, it's going to be what? It's going to be log of products over reactants. That's going to be, so, but we want the conjugate base. That's HPO4 2 minus over top of H2PO4 minus. Okay? So that means 7.02, the pH we want, is equal to 7.198 plus the log of HPO4 2 minus over top of H2PO4 minus. Conjugate base, weak acid. All right, so I subtract this from the other side, and I've got that my log of HPO4 2 minus over top of H2PO4 minus must be equal to 7.82 divided by 7.195 is 0.178. To get rid of the log, what do? I raise both sides to 10, right, to the anti-log, which is 10 to the. So I raise this side to 10 to the, and I get HPO4 2 minus over top of H2PO4 minus is going to be equal to 10 to the negative 0.178, which equals 0.6637. So then I can just distribute this to the other side, and I get HPO4 2 minus is equal to 0.6637 times H2PO4 minus. So what does that tell me? That tells me I can make up this buffer in whatever concentration I want, as long as the amount of HPO4 2 minus is 0.6637 times the amount of H2PO4 minus. Okay, so all I got to do is just figure out what concentration I want and then put those values in, and I'll be able to make that buffer up for that. All right, so again, you're going to be doing the lab, and the lab is pretty simple. All you have to do is hit the button, and the red arrow will move to a certain slot, and I've told you what things to use inside there. I think there's 4 different combinations that you use. And then you just move the sliders till the blue arrow matches up with it, write down those concentrations, and then do the calculation for the Henderson-Hasselbalch equation to verify that that is correct. Other than that, you shouldn't have any problems with it. All right, so again, make sure you get the lab done. Hopefully everything's going okay. If you have any problems, email me. Let me know what's going on. Let me know what you're getting hung up on, what you're getting stuck with, and we'll get it worked out before the lab is due. That's the important thing. Otherwise, I'll see you next week. We're going to do another lab. Have a good one. Try and stay safe and have fun.